June 28, 1944. A narrow strip of English coastline near Dover. Sergeant Thomas Hennessy watched his radar screen with practiced intensity as the green sweep revealed what looked like aircraft approaching from across the channel. But these weren't aircraft. The radar operator for Battery Baker, 390th Anti-Aircraft Artillery Battalion, had seen dozens of them over the past 2 weeks. The signature was distinctive. Single targets, flying straight and level at 320 knots, altitude 2,500 feet, no deviation in course. The Germans called them Vergeltungswaffe 1, Vengeance Weapon 1. The British called them buzz bombs or doodlebugs. Hennessy called them murder. Each one carried 1,800 pounds of amatol explosive toward London, where his sister and her 2 children lived in Bermondsey. The trailer-mounted radar unit beside him, designated SCR-584, had locked onto this particular buzz bomb at a range of 32 miles. The automatic tracking system followed it with mechanical precision as the target closed toward the English coast. Hennessy's job was simply to monitor. The radar did everything else. Range data, bearing, altitude, speed. All transmitted automatically to the M9 gun director 15 yards away, which calculated firing solutions and sent commands directly to 4 90mm guns positioned in a semicircle around the site. The gun crews didn't aim. They simply loaded shells and waited for the guns to fire themselves. At 4 miles range, the guns began tracking. At 2 miles, they opened fire. Hennessy watched the radar display as proximity-fuzed shells detonated around the target. On the 3rd salvo, the buzz bomb's signature vanished from his screen. Another one destroyed before it crossed the coastline. Battery Baker had been operational for 6 days. In that time, they had engaged 42 V-1s. 37 had been destroyed. That morning's engagement brought the total to 38. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The transformation in anti-aircraft effectiveness was nothing short of revolutionary. Just 3 weeks earlier, Britain's gun batteries had been firing 2,500 shells to destroy a single Vone. Now, with the SCR-584 radar system, that number had dropped to 100 shells per kill. Within another month, it would fall to 47. The radar had changed everything. But the story of how a revolutionary American radar system came to defend London from Hitler's vengeance weapons begins not in England, but in a laboratory at MIT, and with a technology the Germans themselves had helped make possible. The genesis of what would become the SCR-584 radar started on September 19, 1940. A small group of British scientists arrived at the Manhattan apartment of Alfred Lee Loomis, a wealthy American physicist who ran his own private laboratory. They had travelled aboard a ship that crossed the Atlantic under constant threat of U-boat attack. Their cargo was considered so valuable that it was kept in a locked metal box chained to the wrist of their leader, Sir Henry Tizard. What they carried would change the course of the war. Inside that box was a cavity magnetron, a radio tube no larger than a man's fist. The British had invented it at the University of Birmingham. It could generate powerful microwave pulses at 10 centimeters wavelength, something American scientists had been trying to achieve for years without success. London was burning under nightly Luftwaffe raids. German U-boats were strangling British supply lines in the Atlantic. Britain needed America's industrial capacity to turn their scientific breakthroughs into weapons that could be produced in quantities vast enough to matter. The Tizard mission, as it became known, represented Churchill's calculated gamble. Give America your most valuable secrets in exchange for their manufacturing capability and hope that would be enough to survive. Loomis examined the magnetron with growing excitement. This device made precision radar practical for the first time. Shorter wavelengths meant tighter beam focus, Tighter beams meant greater accuracy. Greater accuracy meant radar could do more than detect. It could aim. Within weeks of seeing the magnetron, Loomis had arranged funding through the National Defense Research Committee and established a new laboratory at MIT. The radiation laboratory, called the RAD Lab, opened in November 1940 in Building 4 at MIT. Director Lee Dubridge assembled a team of the finest physicists America could provide. Rabi, who would later win the Nobel Prize, served as deputy director. The British sent E.G. Bowen as their representative. Even before the lab officially opened, the founders had identified their three priority projects. First, a 10-centimetre detection system for fighter aircraft. Second, a 10-centimetre gun aiming system for anti-aircraft batteries. Third, a long-range navigation system. The second project, gun-laying radar, would eventually become the SCR-584. It was the most ambitious of the three. Everyone understood that detecting enemy aircraft was only half the battle. Killing them required accurate fire control. Existing American radar, the SCR-268, used long wavelength signals that could only provide approximate location data. It wasn't precise enough to directly aim guns. Anti-aircraft batteries still relied heavily on visual sighting and mechanical predictors that required skilled operators making constant manual adjustments. At night or in cloud, effectiveness dropped dramatically. The Germans had demonstrated the problem's importance in the most brutal way possible. During the Blitz from September 1940 to May 1941, Luftwaffe bombers killed 43,000 British civilians. British anti-aircraft defences, despite thousands of guns and searchlights, shot down relatively few raiders. The mathematics were stark. British gun batteries fired hundreds of thousands of shells to achieve each kill. Most shells simply exploded harmlessly in empty sky. What the Allies needed was a radar system that could automatically track aircraft with enough precision to aim guns directly. Every element of the fire control process needed to be automated. Search, acquisition, tracking, ranging, leading the target to account for its movement, all of it happening faster than human operators could manage. The RAD Lab team, led by Lee Davenport, approached the problem systematically. They would use the magnetron's microwave capability to create narrow, precise radar beams. They would implement automatic tracking using servo mechanisms, electric motors that would keep the radar dish pointed at the target without human intervention. They would calculate range to within a few meters using sophisticated display systems, and they would transmit all this data electronically to a computer that would calculate firing solutions. The concept was called conical scanning. The radar beam would rotate around the antenna's axis, tracing a cone shape. When the beam was pointed slightly off target, the return signal would vary as the beam rotated. By measuring these variations, the system could determine exactly which direction to move the antenna to point directly at the target. Motors would automatically adjust the antenna position, keeping the radar locked on. Alfred Loomis himself proposed this approach in October 1940 for the wholly automatic tracking radar project. German engineers were already using conical scanning in their Würzburg radar, but the SCR-584 would develop the system much further, adding fully automatic operation that required no human guidance once a target was acquired. By April 1941, Davenport's team had a prototype running. To test the automatic aiming capability, they mounted the radar outputs to a gun turret taken from a Boeing B-29 bomber. They removed the guns and replaced them with a camera. The camera would photograph whatever the radar was tracking, proving whether the automatic aiming actually worked. The tests exceeded expectations. The radar could acquire targets, lock onto them automatically, track them with precision, and provide aiming data accurate enough to point guns directly at moving aircraft. While the RAD Lab worked on radar, Bell Telephone Laboratories in New Jersey tackled the even more complex problem of computing firing solutions. Dr. David Parkinson at Bell Labs had literally dreamed the solution. In late 1940, he experienced a vivid dream in which he operated a gun director that automatically tracked enemy aircraft and fired at them with perfect accuracy. He woke convinced the dream represented a feasible engineering solution. He spent the next weeks working with his supervisor, drafting specifications for an analog computer that could calculate everything needed for accurate anti-aircraft fire. Course and speed of incoming aircraft, shell velocity and fuse timing, powder temperature affecting propellant burn rate, shell drift caused by rotation, air density and wind affecting trajectory. The computer would take electrical inputs from the radar and output electrical commands to servo motors that would physically aim the guns. Bell Labs submitted their proposal to the National Defense Research Committee. The project was approved in December 1940. Dr. Parkinson and Clarence Lovell, under the direction of Edward Wente, built the first prototype designated 10. It was delivered to the Army just days after the Pearl Harbor attack. A few hundred units were immediately ordered. As the SCR-584 radar developed, it was paired with what Bell Labs now called the M9 gun director. The WM9 could control 4 standard 90mm anti-aircraft guns simultaneously. On April 1, 1942, the complete system was demonstrated at a Bell Labs facility, radar, computer, and guns working together as an integrated whole. The demonstration was so successful that a contract for over 1,200 systems was issued the next day. The SCR-584 was extraordinarily advanced for its era. The system operated at frequencies between 2700 and 2800 MHz, 10 to 11 centimeter wavelengths. It transmitted 300 kilowatt pulses, lasting 8 microseconds at a rate of 1707 pulses per second. The 6-foot diameter dish antenna could detect bomber-sized targets at 40 miles and automatically track them at 18 miles. Range accuracy was 25 yards. Bearing accuracy was 0 to 6 degrees, 1 mil in military terminology. That precision was revolutionary. Previous radar systems measured target location in hundreds of yards. The SCR-584 measured it in tens of feet. The system included multiple operating modes. For search, the antenna performed helical scanning, rotating at 4 RPM while nodding up and down to scan vertically. Operators watched a PPI display, plan position indicator, that showed targets as bright spots on a circular screen. Once a target was identified, operators could switch to tracking mode. The antenna would lock on to the target automatically and follow it regardless of speed or maneuvering. 2 J-scope displays provided precise range information. One display showed a course range out to 18 miles. The other, with a sweep 16 times faster, allowed operators to determine exact range by positioning a cursor at the center of the return pulse. This pinned down the target distance to within 3 meters. The entire system fit into a single mobile trailer that could be towed by a truck. A separate trailer housed the M9 Director. 490mm guns on mobile mounts completed the battery. The whole system could be operational within hours of arriving at a new location. Production began in earnest in late 1942. 3 manufacturers shared the work: Westinghouse, General Electric, and Chrysler. By mid-1943, production reached 2,000 units per month. Yet, despite this manufacturing success, the SCR-584 faced bureaucratic obstacles that delayed its deployment to combat units. The first operational unit was delivered in May 1943, but various administrative problems kept it from reaching frontline troops for months. That delay would finally end when the situation in Italy became desperate enough that innovative solutions could no longer be ignored. The SCR-584 was first used in combat at Anzio in February 1944. The amphibious landing, intended to outflank German defences and threaten Rome, had instead become a deadly stalemate. Allied forces were pinned on. A small beachhead, constantly under German artillery fire and air attack. German and Italian air forces had found they could jam the older SCR-268 radars, rendering them nearly useless. Night bombing raids hit the crowded beachhead and harbour with impunity. On February 24th, 2 complete SCR-584 systems were rushed to Anzio aboard fast transport ships. They were unloaded under fire and emplaced overnight, dug in up to their trailer rooftops for protection. The next night, 12 German bombers entered the beachhead airspace. The SCR-584 radars tracked them automatically. M9 directors calculated firing solutions. 90mm guns, loaded with conventional time-fused shells, opened fire. 7 of the 12 bombers were destroyed. The survivors fled. German air attacks stopped for a week. A single reconnaissance aircraft appeared days later to test the defences. The SCR-584 tracked it. Guns destroyed it before it could report back. 10 more SCR-584 systems were emplaced at Anzio that week. The German air threat to the beachhead effectively ended. What had been a shooting gallery for German bombers became a death trap, but the system's true test was still to come. That test would arrive on the morning of June 13, 1944, 1 week after D-Day, when Germany launched its first V-1 flying bombs against London. The weapon represented something unprecedented. Not an aircraft with a pilot who could evade or maneuver. Not a ballistic shell following a predictable arc. The V-1 was history's first operational cruise missile, a pilotless aircraft that flew a straight, level course at high speed until its fuel ran out and it plummeted to Earth carrying nearly a ton of high explosive. The first V-1 struck London at 4:20 in the morning on June 13th. It hit the railway bridge at Grove Road in Mile End, killing 8 people and injuring 30. Within hours, more arrived. By the end of that first day, 10 V-1s had struck London. Over the next week, the attacks intensified. Germany launched nearly 100 V-1s daily from sites in occupied France and the Low Countries. The V-1, officially designated Fieseler F-103, was 27 feet long, with a wingspan of 17.5 feet. It weighed 4,762 pounds fully fueled. An Argus pulse jet engine mounted above the fuselage provided thrust. The engine had no moving parts. It fired 45 to 50 times per second, creating the distinctive buzzing sound that gave the weapon its nickname. The pulse jet burned low-octane gasoline mixed with compressed air. Maximum speed was 373 miles per hour at 8,200 feet altitude. Maximum range was 146 miles. The guidance system was brutally simple. A magnetic compass maintained heading, an autopilot controlled pitch and bank, air-driven vanes at the nose spun an odometer that counted distance, travelled. When the counter reached a preset number corresponding to target distance, it shut down the pulse jet. The V-1 entered a steep dive and struck the ground. The warhead, containing 1,830 pounds of amatol explosive, detonated on impact. 3 fuses ensured detonation: an electrical impact fuse, a mechanical impact fuse, and a mechanical delayed action fuse in case the V-1 buried itself before the impact fuses triggered. The weapon was only accurate enough to hit a general geographic area. Germany aimed them at Westminster and the London docks. Most struck somewhere in Greater London, though many fell short in Kent or Surrey. The psychological impact was immense. Unlike conventional bombing raids, which triggered air raid sirens giving people time to seek shelter, V-1s arrived with little warning. Civilians heard the distinctive buzz of the pulse jet, then silence as the engine cut out, then the explosion. The silence was the worst part. When the buzzing stopped, you knew the bomb was falling somewhere nearby. You had perhaps 15 seconds to pray it wasn't falling on you. Civil defense authorities initially tried to conceal what was happening, claiming the explosions were caused by defective gas mains. The public wasn't fooled. They sardonically nicknamed the V-1s flying gas pipes. Between June 13th and August 28th, 1944, Germany launched over 10,000 V-1s toward England. Of these, 7,300 presented credible threats to British defences. The remainder crashed shortly after launch, suffered mechanical failure, or went wildly off course. Britain's response involved three defensive lines. Fighter aircraft over the Channel and English coast would attempt to intercept V-1s in flight. Anti-aircraft gun batteries in Kent would create a barrier of exploding shells. Barrage balloons around London would destroy any V-1s that penetrated the first two layers. Initially, results were disappointing. Fighter interception proved difficult. The V-1 flew faster than most British fighters at low altitude. Only the newest Spitfire Marks, Tempests, and American P-47 Thunderbolts could catch them. Pilots who did catch up found destroying the small, fast-moving target challenging. Many resorted to tipping the V-1's wing with their own wing, destabilizing it and causing it to crash in unpopulated areas. Anti-aircraft guns firing conventional time-fused shells were even less effective. Gunners had to visually spot the V-1, estimate its speed and altitude, calculate a firing solution, aim the gun, and fire, all before the target passed out of range. The V-1's speed meant engagement windows lasted only seconds. Hit rates were abysmal. In the first week of V-1 attacks, gun batteries destroyed only about 17% of the bombs that entered their engagement zone. They were firing 2,500 shells for every V-1 destroyed. The mathematics were unsustainable. Britain had thousands of anti-aircraft guns defending against the V-1 threat. At 2,500 shells per kill, ammunition consumption was enormous. More critically, thousands of V-1s were getting through to London. The civilian casualties mounted rapidly. In the first month of attacks, over 2,400 V-1s struck the London area. 6,184 people were killed. 17,981 were seriously injured. 20,000 houses per day were being damaged at the height of the campaign, creating a massive housing crisis across southeastern England. Something had to change. The answer was already in production, already proven in combat at Anzio, but not yet deployed in sufficient numbers for the V-1 threat. The SCR-584 radar system. Churchill himself intervened. He pleaded with American commanders to release SCR-584 units that had been designated for the continent following the D-Day invasion. The situation was desperate enough that he also requested something even more closely guarded. Proximity fuses. The proximity fuse represented another American technological triumph developed in secrecy. Unlike conventional time fuses that exploded after a preset number of seconds, proximity fuses contained miniature radio transmitters and receivers. When the shell passed close to a target, the fuse detected the echo of its own radio signal bouncing off the target and detonated the shell automatically. This eliminated the need to calculate precise fuse timing. A shell equipped with a proximity fuse simply needed to pass within lethal range of the target. The explosion would happen automatically at the optimal moment. Development of proximity fuses had been highly classified. The United States feared that if one landed unexploded in enemy territory, the Germans would copy the technology. For this reason, proximity fuses had been used primarily over water, where duds would sink and couldn't be recovered. Churchill argued that V-1 defence met this criteria. Shells would fall either in the Channel or on British soil, where recovery teams could secure any duds before German agents could reach them. American commanders agreed. In late June 1944, SCR-584 radar units began arriving at gun batteries along the English coast. They came with M9 directors and supplies of proximity-fused shells. The gun batteries were relocated from their previous positions inland to form a continuous belt along the coast. This prevented shells from falling on British homes and ensured any unexploded proximity fuses would land where they could be recovered. The new defensive arrangement placed fighters over the Channel and the English coast. The gun belt came next, stretching along the coast where V-1s crossed from France. Barrage balloons formed the final defence around London itself. RadLab engineers Leo Sullivan and Lee Davenport travelled to England to train the gun and radar crews on the SCR-584 systems. The training was intensive but brief. The SCR-584 was remarkably simple to operate once crews understood the basic procedures. The radar performed search automatically in helical scan mode. When operators spotted a target on the PPI display, they switched to tracking mode. The radar locked on automatically. From that moment, the system required no further human input. The radar tracked, the M9 director calculated, the guns aimed and fired. Crews simply loaded shells and watched as the system destroyed target after target. The transformation in effectiveness was immediate and dramatic. In the first week of coastal operations ending July 2nd, gun batteries destroyed 17% of V-1s entering the gun belt. 1 week later, that number had jumped to 24%. By July 23rd, it reached 60%. On August 23rd, the success rate hit 74%. On August 28th, in what would prove to be the final day of the V-1 campaign launched from France, the gun batteries achieved 82% kills. Of 104 V-1s launched that day, gun batteries destroyed 64. Fighters accounted for 14 more. Only 4 reached London. The cost in ammunition had also dropped dramatically. In early July, gun batteries fired 2,500 shells per V-1 kill. By late July, that number had fallen to 100 shells per kill. By late August, it was below 50 shells per kill. The SCR-584's automatic tracking and precision ranging made this possible. The system could detect a V-1 at ranges exceeding 30 miles. It locked on automatically and tracked the target continuously as it approached. The M9 director received constant updates on target position, speed, and heading. It calculated firing solutions accounting for shell ballistics, air density, wind, and the time it would take for the shell to reach the intercept point. Proximity fuses eliminated the final variable. Even if calculations were slightly off, if the shell passed anywhere near the V-1, the fuse would detonate it. The combination was devastating. British gun crews, many of whom had served through years of frustrating ineffectiveness against German bombers during the Blitz, suddenly found themselves destroying target after target. Flight Officer David Williams, a radar operator with 413th Battery, kept a diary during the V-1 campaign. His entry from August 15th captures the transformation. We locked onto 12 V-1s today between dawn and dusk, destroyed 11. The one that got through suffered engine failure and crashed in the channel. The system is extraordinary. The moment we get radar contact, it's essentially over for the buzz bomb. The radar tracks automatically no matter how fast it flies. The director solves everything instantly. The guns fire the moment they're in range. The proximity fuses do the rest. I watched. One engagement this afternoon. Target appeared on screen at 28 miles. Locked on at 23 miles. Guns engaged at 4 miles. Third salvo destroyed it at 2.3 miles. The whole engagement lasted maybe 90 seconds from detection to kill. Williams would later note that the psychological effect on the gun crews was as significant as the tactical success. For the first time, they were winning. The transformation extended beyond mere statistics. In late June, British gun batteries destroyed about 17% of V-1s entering their engagement zone. A single week later, that figure jumped to 24%. By July 23rd, it reached 60%. August 23rd saw 74% destroyed. The final day of the initial V-1 campaign from France, August 28th, produced the most remarkable results. Of 104 V-1s launched, gun batteries destroyed 64. Fighters accounted for 14 more. Only 4 reached London. The mathematics were stark. In early July, destroying a single V-1 required 2,500 shells. By late July, that number had collapsed to 100 shells per kill. By late August, it stood below 50. The SCR-584's precision tracking, combined with proximity fuses and the M9 director's calculations, had revolutionized anti-aircraft warfare. One particular Sunday demonstrated the system's effectiveness with brutal clarity. On that day, of 101 V-1s launched toward England, gun batteries destroyed 97. 4 V-1s penetrating 3 defensive lines represented a success rate unprecedented in the history of air defense. British civilians, who had endured weeks of terror as V-1s rained down with minimal opposition, noticed the change immediately. Margaret Turner, a schoolteacher in Croydon, kept a diary during the Vone campaign. Her entry from late August reflected the psychological transformation. For weeks we heard them, constantly. That horrible buzzing, then silence, then the explosion somewhere nearby. Every time, wondering if this would be the one. Now we hear the guns almost continuously, and we know they're hitting them. My students ask why there are fewer explosions in London now. I explain that brave soldiers with clever machines are destroying the bombs before they reach us. The children cheer. We all cheer. For the first time since June, I believe we might survive this. The SCR-584's success against V-1s demonstrated principles that would shape military technology for decades. Automatic tracking eliminated human reaction time delays. Precision ranging allowed exact calculation of intercept points. Electronic fire control removed aiming errors. Proximity fuses compensated for small trajectory variations. The integrated system performed functions that no single component could achieve alone. German military intelligence recognized the implications immediately. Luftwaffe reports from August 1944 noted dramatic increases in Vone losses over the English coast. German analysts correctly identified radar-controlled anti-aircraft fire as the primary cause. They understood that the Allies had deployed sophisticated fire control systems that German technology could not yet match. One captured Luftwaffe intelligence document, translated by British codebreakers, contained a remarkably accurate assessment. The enemy has deployed automatic tracking radar systems along the Channel coast. These systems provide fire control data of unprecedented accuracy. Our Vergeltungswaffe 1's losses have increased to unsustainable levels. Current defensive arrangements cannot be maintained. The German assessment was correct on all counts. By late August 1944, Allied forces advancing through France had overrun the Vone launching sites. The campaign, launched from fixed ground installations, ended on August 29th. Germany attempted to continue Vone attacks, using air-launched versions carried by Heinkel He, 111 bombers, but these proved even less effective. Fighter interception destroyed most air-launched V-1s before they could be released. The Vone threat to England effectively ended in September 1944. In total, approximately 10,000 V-1s were launched toward England between June 13th and the campaign's end. Of these, 7,400 crossed the British coast as viable threats. British defences destroyed approximately 4,000. Fighters accounted for roughly 2,000 kills. Anti-aircraft guns destroyed approximately 1,600. Barrage balloons brought down about 230. The remaining 3,400 struck England, with 2,400 hitting the London area specifically. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The human cost was severe. In London, 6,184 people died from Vone impacts. 17,981 suffered serious injuries. V-1s damaged or destroyed thousands of homes daily at the campaign's height. 20,000 houses per day were being damaged in July, creating a massive housing crisis across southeastern England. But without the SCR-584, casualties would have been far worse. Statistical analysis suggests that if the gun belt had maintained its early July effectiveness throughout the campaign, an additional 1,500 to 2,000 V-1s would have struck London. Each Vone carried 1,800 pounds of explosive. Each typically damaged or destroyed 400 houses and killed or injured dozens of people. The SCR-584's deployment prevented thousands of additional civilian deaths. The system's effectiveness extended well beyond the Vone campaign. After Allied forces liberated Belgium in September 1944, Germany redirected Vone attacks toward Antwerp. The port city was crucial to Allied logistics. Germany launched approximately 2,400 V-1s against Antwerp between October 1944 and March 1945. SCR-584 systems defended Antwerp just as they had defended London. The results were similar. Gun batteries achieved high kill rates. The port continued operating despite sustained attacks. The SCR-584 also proved valuable for entirely different applications. In December 1944, Germany launched its final major offensive of the war, the Battle of the Bulge. German forces achieved tactical surprise, breaking through American lines in the Ardennes forest during terrible weather that grounded Allied aircraft. For several days, only radar-directed operations could function. SCR-584 units tracked friendly aircraft through clouds and guided them to targets. They detected German vehicle movements at ranges exceeding 26 kilometers. They tracked artillery, shells in flight, allowing American forces to calculate precise trajectories and pinpoint German battery positions for counter-battery fire. One SCR-584 operator with the 7th Armored Division later described the system's versatility. "We started the war thinking this was an anti-aircraft radar. By the Bulge, we were using it for everything, tracking our own planes through cloud to guide them onto targets, spotting German tank columns before they were visible, finding German artillery positions by tracking their shells. The system did things the designers never imagined." General George Patton's Third Army, racing north to relieve besieged Bastogne, relied heavily on SCR-584 directed air support during the relief operation. The radars allowed tactical aircraft to operate effectively, despite weather that would normally have grounded them. The production numbers reflected the system's importance. By the time Dodge Division delivered the final SCR-584 from the primary production run on January 28, 1944, 2,908 sets had been manufactured. Westinghouse, General Electric, and Chrysler had shared production responsibilities. Each system represented approximately 10,000 work hours across all subcontractors. The manufacturing effort mobilized 32 separate suppliers, providing specialized components. Magnetrons from Raytheon, transmitters from Western Electric, display tubes from various electronics manufacturers, precision mechanical components from dozens of machine shops. The supply chain complexity rivaled that of much larger weapons systems. Cost effectiveness was remarkable. Each complete SCR-584 system, including the radar trailer, antennas, and all electronics, cost approximately $45,000 in 1943 dollars. The M9 gun director added another $30,000. 4 90mm guns and their mobile mounts added roughly $60,000. A complete fire unit, capable of defending several square miles of airspace and engaging multiple targets, cost approximately $135,000. By comparison, a single B-17 bomber cost $200,000. A heavy cruiser cost $50 million. The SCR-584 provided capabilities that dramatically enhanced the effectiveness of existing weapons at a fraction of the cost of new platforms. The system's operational lifespan extended far beyond World War II. The basic SCR-584 remained in American service through the Korean War. Modified versions served with NATO forces into the 1960s. Some countries used upgraded SCR-584 derivatives into the 1970s. The fundamental principles remained sound: automatic tracking, precision ranging, electronic fire control. These concepts, proven by the SCR-584, became standard features of every subsequent fire control radar. Modern air defense systems trace their lineage directly to the MIT Radiation Laboratory's wartime work. The Patriot missile system that defended against Iraqi Scud missiles in 1991 used automatic tracking and fire control concepts pioneered by the SCR-584. The Aegis combat system aboard modern cruisers and destroyers uses phased array radar that evolved from wartime microwave radar research. Even civilian applications emerged. Post-war, SCR-584 units were modified for weather tracking. The National Weather Service used converted military fire control radars for storm detection until purpose-built weather radars replaced them in the 1960s. Air traffic control radar evolved from military search and tracking systems developed during the war. The human story behind the SCR-584 encompasses both triumph and tragedy. The engineers and scientists who developed the system worked under intense pressure. Lee Davenport's team at the radiation laboratory typically worked 6 days per week, often extending into evenings. The laboratory operated on the principle that every month of delay cost lives. That urgency drove innovation but exacted personal costs. Several engineers suffered nervous exhaustion. Marriages strained under the pressure. Dr. Alfred Loomis, whose proposal for conical scanning became fundamental to the SCR-584's design, continued funding radar research from his personal fortune even as the government project expanded. His Tuxedo Park laboratory had served as an unofficial research center before the radiation laboratory opened. Loomis represented a particular type of American innovation, the wealthy private citizen who directed personal resources toward problems he considered vital to national survival. Without his initial work and advocacy, the magnetron might have arrived in America without anyone prepared to exploit its potential. The radiation laboratory itself represented a remarkable concentration of scientific talent. At its peak, it employed nearly 4,000 people, including many who would later win Nobel Prizes or make fundamental contributions to post-war science. Luis Alvarez developed radar landing systems. Norman Ramsey worked on radar countermeasures. Robert Oppenheimer consulted on various projects before moving to Los Alamos. The laboratory's work extended far beyond the SCR-584. They developed airborne intercept radar that transformed night fighter effectiveness. They created navigation systems that allowed aircraft to find targets in darkness and bad weather. They produced systems for detecting surfaced submarines. They developed ground-mapping radar that revealed enemy positions through clouds. The radiation laboratory's total contribution to Allied victory is difficult to quantify but undoubtedly significant. Post-war analysis suggested radar, in its various applications, shortened the war in Europe by at least 6 months, possibly a year. That acceleration saved countless lives, both military and civilian. The laboratory closed in December 1945. Staff dispersed to universities, industry, and government laboratories. Many continued working on radar and electronics, spreading the knowledge gained during the war. The MIT Radiation Laboratory Series, a comprehensive 28-volume technical documentation of wartime radar work, was published between 1947 and 1953. These volumes became fundamental references for a generation of engineers and scientists. The SCR-584 received detailed coverage across multiple volumes. Technical descriptions, operational procedures, design principles, everything was documented and made available to researchers worldwide. This openness represented a deliberate choice. American policymakers decided that scientific knowledge should be shared, even with potential adversaries, because long-term American security depended on maintaining technological leadership through continued innovation rather than secrecy about past achievements. That policy proved remarkably successful. American radar technology led the world for decades after the war, not because secrets were kept, but because the infrastructure for continued innovation remained robust. The legacy of specific individuals deserves recognition. Dr. Lee Davenport, who led the SCR-584 development team, received the Presidential Medal for Merit in 1948. I. Rabi, who served as Deputy Director of the Radiation Laboratory, won the Nobel Prize in Physics in 1944 for work on magnetic resonance research he had conducted before the war, while also contributing to radar development. Dr. David Parkinson and Clarence Lovell, who developed the M9 gun director at Bell Telephone Laboratories, received numerous awards and continued working on fire control systems after the war. Their analog computer, designed before digital computers existed, represented a remarkable achievement in mechanical calculation. The M9 could solve complex ballistics equations in real time, accounting for dozens of variables, using only gears, cams, and electrical motors. The hundreds of thousands of shells fired by SCR-584 directed guns tell their own story. Each shell represented American industrial capacity. The proximity fuses alone required sophisticated manufacturing. Each fuse contained a miniature radio transmitter, receiver, and detonator in a package small enough to fit in a shell that would be subjected to 15,000 times the force of gravity during firing. Manufacturing these devices required developing entirely new production techniques. By late 1944, American factories produced 70,000 proximity fuses daily across various calibers. The production achievement matched the technical achievement. Without mass production, brilliant designs remained laboratory curiosities. The SCR-584 succeeded because American industry could manufacture complex electronics in quantity. That capability, more than any single technical breakthrough, determined war's outcome in numerous applications. German scientists often matched or exceeded American theoretical understanding. German radar in some applications equaled or surpassed Allied equivalents. But Germany could not match American production capacity. The SCR-584 succeeded not just because it was well designed, but because America could build 2,900 of them and supply millions of shells with proximity fuses. The story of the SCR-584 intersects with broader narratives about how World War II changed warfare fundamentally. The integration of radar, computing, and automated fire control represented a transition from human-directed to machine-assisted combat. Future wars would increasingly involve systems rather than individual weapons. The SCR-584 exemplified this transition. No single component could defeat V-1s effectively. The radar alone simply detected them. The M9 director alone could not track them. The guns alone could not aim accurately enough. The proximity fuses alone provided no targeting data. Only the complete integrated system achieved the results that transformed air defense. This systems integration approach dominated post-war military development. Modern combat aircraft are not simply fast planes with guns, but integrated platforms combining sensors, computers, weapons, and countermeasures. Modern warships are floating networks of radars, missiles, and electronic warfare equipment, all coordinated by computers. The SCR-584 pioneered this integration. From a technological perspective, the most remarkable aspect may be how quickly it was developed. From the magnetron's arrival in America in September 1940 to operational deployment in February 1944 took less than 3.5 years. That included developing the basic technology, engineering a production design, establishing manufacturing infrastructure, training operators, and deploying to combat zones. No comparable modern program achieves similar speed. The Joint Strike Fighter program took nearly 2 decades from initial concept to operational deployment. Modern weapons development involves extensive requirements analysis, multiple prototype iterations, comprehensive testing, and bureaucratic oversight that extends timelines dramatically. The wartime urgency that drove SCR-584 development has no peacetime equivalent. This raises questions about whether modern military development processes serve their intended purposes. Careful, deliberate development reduces risks and ensures thorough testing, but extended timelines mean weapons may be obsolete before deployment. The balance between speed and thoroughness remains contentious. The SCR-584 demonstrated that rapid development was possible when necessity demanded it and when bureaucratic obstacles were minimized. German reactions to the SCR-584's effectiveness were mixed. Some German officers recognized that Allied technology had achieved decisive advantages in specific applications. Others attributed Allied success primarily to material superiority rather than technical sophistication. Both perspectives contained truth. The Allies did possess material advantages, American industrial capacity produced weapons, vehicles, and ammunition in quantities Germany could not match. But that material advantage was amplified by technical innovations like the SCR-584 that multiplied the effectiveness of existing weapons. A gun battery equipped with SCR-584 radar achieved destruction rates 6 times higher than the same guns with older fire control systems. That multiplier effect, repeated across numerous weapon systems, contributed significantly to Allied victory. The V-1 campaign itself represented Germany's attempt to achieve strategic impact through technological innovation, despite resource limitations. Each V-1 was relatively inexpensive to produce. Germany built approximately 30,000 V-1s during the war. Production required minimal materials compared to conventional bombers. The pulse jet engine had no moving parts, simplifying manufacturing. The guidance system was crude but adequate for targeting large urban areas. From Germany's perspective, V-1s represented economical weapons that could inflict damage disproportionate to their cost. That calculation proved incorrect once the Allies deployed effective countermeasures. The SCR-584 negated Germany's investment in V-1 production by making the weapons ineffective. Thousands of V-1s were destroyed short of their targets. The resources invested in producing them were wasted. This pattern repeated throughout the war. Germany invested heavily in wonder weapons, advanced technologies intended to compensate for material disadvantages. Some, like jet aircraft and ballistic missiles, showed promise but arrived too late or in too small numbers. Others, like the V-1, were effectively countered by Allied technology. The lesson for military planners was that technological innovation required sustainable production and effective deployment, not just clever engineering. The SCR-584's post-war influence extended into unexpected areas. The automatic tracking systems developed for radar found applications in satellite ground stations. Early space tracking facilities used modified SCR-584 units. The precision pointing required to track satellites resembled the precision needed to track aircraft. Engineers familiar with SCR-584 technology adapted their knowledge to new challenges. Similarly, the servo control systems that kept SCR-584 antennas pointed at targets influenced the development of industrial robotics. The basic principle of using electrical signals to control mechanical motion with precision found numerous civilian applications. Machine tools, manufacturing equipment, even camera tracking systems for television studios borrowed concepts from wartime fire control radars. The Radiation Laboratory's broader legacy included training a generation of engineers and physicists who dominated post-war technology development. Many Rad Lab veterans moved to emerging electronics companies. They founded new firms that became leaders in semiconductors, computers, and telecommunications. The Silicon Valley phenomenon of the 1960s and 70s had roots in wartime radar laboratories, where young engineers learned to push technology boundaries under extreme pressure. The human cost of the V-1 campaign remained significant despite the SCR-584's effectiveness. Over 6,000 British civilians died from V-1 impacts. Another 18,000 suffered serious injuries. Tens of thousands lost their homes. Entire neighborhoods were devastated. The psychological impact extended beyond physical casualties. The unpredictable nature of V-1 attacks, the silence after the engine stopped followed by explosion, created pervasive anxiety across London and southeastern England. Civil defence workers, medical personnel, fire brigades, all operated under constant threat. The dedication of these civilians, who maintained essential services despite danger, deserves recognition alongside the technical achievements that eventually ended the threat. The radar operators and gun crews who manned the coastal defence belt faced their own challenges. They worked long shifts in all weather, tracking and engaging targets with knowledge that every miss might mean civilian deaths in London. The pressure was intense. Battery Baker, where Sergeant Hennessy operated his SCR-584, engaged V-1s almost daily from late June through August. The crew developed routines, But the weight of responsibility never diminished. Each successful engagement meant people saved. Each miss meant potential tragedy. Post-war, many veterans of the V-1 defense campaign reflected on their experiences with pride tempered by awareness of what had been at stake. Thomas Hennessy, the radar operator whose engagement opened this story, completed his service and returned to Pennsylvania in 1946. He worked as an electrical engineer for Westinghouse for 37 years. In interviews late in his life, he spoke about the SCR-584 with pride. "We knew we had something special. The radar worked like nothing else existed. When we locked onto a target, we owned it. The Germans probably thought we had magic. Really, we had brilliant engineers and excellent training." That professionalism, combined with remarkable technology, saved thousands of lives. The SCR-584 story encompasses multiple themes that resonate beyond its specific technical achievements. It demonstrates how the crisis accelerates innovation. The Tizard mission succeeded because Britain faced existential threat. The radiation laboratory accomplished in months what might normally take years because delay meant more deaths. Modern peacetime development lacks that urgency, for better and worse. It reveals how systems integration creates capabilities exceeding individual components. The radar, director, guns, and fuses each contributed essential functions. Together, they revolutionized air defense. This principle underlies all modern military technology. It shows how manufacturing capacity transforms technical advantage into strategic impact. The SCR-584's brilliant design mattered because America could build thousands of them. Innovation without production remains theoretical. It illustrates how technology transfer between allies multiplies effectiveness. British magnetron technology, combined with American manufacturing, created capabilities neither nation could achieve alone. International cooperation, despite its complications, produces results. It confirms that defending populations from attack requires integrated approaches, combining detection, interception, and destruction. No single solution suffices against evolving threats. Layered defenses, constantly updated to match new threats, provide the only reliable protection. The SCR-584 defended against the first operational cruise missiles. Modern air defenses face far more sophisticated threats: stealth aircraft, supersonic missiles, drone swarms, hypersonic weapons. Each new threat requires new countermeasures. The fundamental challenge remains unchanged. Detect incoming threats at maximum range, track them precisely, calculate intercept solutions, engage before they reach targets. The SCR-584 demonstrated these principles work when executed with sufficient technical sophistication. 8 decades later, those same principles guide air defense systems worldwide. The descendants of the SCR-584, systems with names like Patriot, THAAD, and Iron Dome, defend against modern threats using technologies the RadLab engineers could never have imagined. But the fundamental concepts they pioneered remain valid. From a cramped radar trailer on the Dover Cliffs to modern phased array systems tracking ballistic missiles, the technological lineage is clear. Joan Curran's window strips, described in a previous story, blinded radars. The SCR-584 proved radars could see through the chaos and maintain lock on targets. These competing technologies, countermeasure versus countermeasure, continue evolving. The electronics warfare battle between detection and evasion will likely continue as long as nations possess military capabilities. The SCR-584's legacy is not just technical. It represents a particular moment when America mobilized scientific and industrial resources to solve urgent military problems. That mobilization succeeded because talented people were given clear objectives, adequate resources, and minimal bureaucratic interference. They delivered results that changed warfare fundamentally. Whether modern systems could replicate that achievement remains uncertain. Contemporary weapons development faces different challenges. Threats are more diverse and sophisticated. Political and budgetary constraints are more complex. Public scrutiny is more intense. Risk tolerance is lower. But the fundamental principle remains valid. When brilliant people focus on important problems with adequate support, they produce remarkable results. The radiation laboratory demonstrated this principle. Their legacy challenges modern institutions to maintain similar focus and effectiveness despite peacetime complications. The men who operated SCR-584 systems seldom spoke about their service in dramatic terms. They described routine work performed under pressure, training and practice until procedures became automatic. Long shifts, watching screens and maintaining equipment, brief moments of intense activity when targets appeared, then more waiting. But their routine work, multiplied across dozens of batteries and thousands of engagements, saved lives measurably. The statistical evidence is clear. When SCR-584 systems deployed against V-1s, destruction rates increased dramatically. More V-1s, destroyed before reaching London, meant fewer explosions, fewer casualties, less destruction. The mathematics of survival favored those who benefited from the radar's protection. Thomas Hennessy watching his screen in Battery Baker. The gun crews loading 90mm shells. The engineers who designed the system. The workers who manufactured it. The scientists who developed the underlying technology. Each contributed to an integrated effort that demonstrated how technology, properly applied, protects people from harm. That protection came at the cost of years of intensive development, billions of dollars in resources, and the coordinated effort of thousands. But for the 6,000 British civilians who did not die because V-1s were destroyed short of London, for the 18,000 who did not suffer injuries, for the families whose homes were not destroyed, that protection justified every dollar spent and every hour invested. The SCR-584 represents applied science at its most consequential. Not abstract theory, but practical technology that changed outcomes in the most concrete terms imaginable. People lived who would have died. That simple measurement of success transcends technical specifications and operational statistics. Innovation matters ultimately because it affects human lives. The SCR-584 affected thousands of lives directly and shaped the development of technologies that continue protecting people today. From Dover cliffs in 1944 to modern air defense networks worldwide, the technological lineage remains unbroken. The principles proven there, automatic tracking, precision fire control, systems integration, continue evolving but remain fundamentally sound. And somewhere in every modern air defense system, whether acknowledged or not, lives the legacy of MIT engineers who worked through the night, Bell Labs computer designers who dreamed of automated fire control, radar operators who watched green screens with practiced intensity, and gun crews who loaded shells, while V-1s approached at 300 miles per hour. Their work saved lives. Their legacy endures. Their achievement reminds us that technology, properly applied with clear purpose and adequate resources, can protect the vulnerable from those who would do them harm. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.